Okay, so now it's recording, and because there's no videos, they can only see the board. So the first thing I'm going to talk about is quickly give you an overview of my background. So you guys got a bit of knowledge where I am from. I don't know if you can see it from there or if you want to come closer, it's up to you. Okay, so basically this is where I was born, a country in the westernmost country in Africa. So I don't know if you know, if you're good in your geography a wee bit. No? Do you know where Sadio Mane is from? Yeah. So that's where I was born. He was born closer to Gambia because it's from the south, but I was born in Senegal. The capital is Dakar. So if someone asks you the westerly point of Africa, the point closest to America is Dakar. Okay. I spent there 17 years. And after that, I went to, this is not working. After that, I went to spend 4 years in France to do electronics. Okay, so that might help you a wee bit. So if you've got any questions during your electrical courses, I can always help you out. Okay, then after that, I spent 2 years in Grenoble to do microelectronics, working with microchips. So I don't know if you guys seen a wafer before. So this is what we call a wafer. A wafer is where you build all those microchips and then you test them before you put them into these wee IC circuits. You might have heard about them, okay? But that was most of my background. Then I had to do a 1-year military service in the French Air Force. And that's where I started teaching the first time. So I taught basic electronics. Okay, so any AC, DC type circuits, but in the electronic world. So I spent a year in the military Air Force. So you do both. You do a bit of drill work and then teach at the same time. And then I came to UK. So I spent about a year and a half in the school. I was a lab technician there. That's where I started, because if you look at it, these places, which country these places are in? Marseille, France. So all my study was done in French because Senegal was a former French colony. Okay, so that's why. Then when I came to Windsor, I started learning a bit of, or applying more of my English that I learned at school into there, which is easy enough for me. And then I joined a company called Motorola. Do you remember one of the phones? Flip-flop phones were the first ones that was made by Motorola. And that was in East Kilbride. Have you heard about East Kilbride? Not far from here, 25 minutes down south. And after spending 22 years there, the company got bought by a company that used to be called Philips Semiconductor. So they make, again, chips. It's called NXP now. They bought us and asked us to move our division in Austin, Texas. So it was either that or you take the package. And because you spend quite a lot of time in the company, usually the package is quite good. So they give you a package so that you don't take them to, you know, unfair dismissals, blah, blah, blah. So I took the package and went back to uni to do a postgrad diploma for education to allow me to teach. So as you can see, my background is more like physics, electricity, electronics. So I'm first a science teacher. So physics is my background, but then I did what we call a dual qualification at UWS. So they gave me that chance to do that. And the other qualification I took was to do math. And that's why I'm here today. But in those times, I've spent time in most of my, what we call a newly qualifying teacher's career. So my first year I spent at St. Joseph Academy in Kilmarnock. Do you guys know about Kilmarnock? No? So it's down on the coast there, East Ayrshire, and then Kilmarnock Academy. I went to Stewarton as well on placement. Grange Academy, famous football player that was there. Young guy, Chelsea, then moved. So that's where he graduated, because Grange Academy had a football scheme. You've heard about some schools in Scotland, they do both football and so I was there when he was doing his National 5 at Grange. So they were doing a bit of during the day sports. So it's mixed basically of both, okay? And then that's why I'm here, because I've been teaching in like math in evening classes for Glasgow Clyde College. And this year I'm doing full time, but during the day. And that's why you've been full time. You've got me today, okay? So what I would say, I've put this as being your best friend for this year. So you're gonna have to source yourself. If you've done higher, you must got a Casio FX or something. Okay, so the other thing I've put there is, you see this NCalc FX. It's a great wee app that is for free. So if you've got your phone, what I would do is I would download this app for free. So it's called NCalc FX. It's got a wee orange background onto it, and use that. So that means even if you are, I don't know, in a train waiting for half an hour, not knowing what to do, and I'll send you this material into PDF, and that means you can do a bit of work. And if you've got your calculator, you can check that with that. So with your phone, you shouldn't be spending time on social media, because we all do it, right? We all waste so much time, whereas your focus this year should be, I need to get these engineering math out of the way. And the best way to do it is to practice a wee bit, okay? And the best way to do it is look at the time that you spend in social media. And if you take half an hour of that time every day and focus a bit of doing a bit of math, that will help you to retain what you need to get to the end, okay? So the problem is, the way we've been learning most of the time is we kind of wait till it's a few days before the exam and start to learn just to be prepared for the exam. But if you do that, you're not going to succeed with this course, okay? Because it needs you to retain information from what you're going to do in block 1, what you're going to do in block 2. And when you get to block 3, they'll still ask you questions from block 1. So it's better to do a bit every day than just everything in a couple of nights to be ready to pass, okay? Plus, you will need a bit of math in everything else you will do, to be honest. Okay. So that's why I've put them in here. So the first thing you've got for this week is looking at sets and functions. Okay. So sets and functions is in your, so you should have in your notes, it's going to be your first chapter to go through. So it's you start at page 3, okay? Page 3 basically, so notation. So what they call a set is a collection of objects, and those objects have got a common property. So what they mean by a common property is they're similar, okay? So those objects, so that's what they call a set. That is how it's defined. So in a set, what we call the items that are inside the sets, we call them members or elements. So if you're asked how many elements have you got in your set, you would say 4 or 5, and they all got something similar about them. Okay, so when we put a set together, we describe them using what we call brackets. So the brackets are going to be like this. So let me see if I can change the color. Yeah, so basically you're going to have an open bracket and a closed bracket, and inside you'll have a set of numbers. So I can say 0, 1, 2, for example. So you've got 3 elements in my set, and we just put brackets. Okay, so that's how it's defined. So now we can describe numbers. So since you've been at primary, you've been using numbers, right? So the first one are what we call the natural numbers. You know, when you were at primary, what did you learn first about math? What were you doing with your fingers? Counting. And you always started with number 1, 2, 3, 4. So that set of all the numbers right up to infinity, we call them natural numbers. Okay, so we call it group N of all the natural numbers, 1, 2, 3, 4, and so on. Okay, so those are the numbers that come more naturally to us. Now, in math, someone decided there is a number that comes before 1 that's quite useful, 0. So in order to put that, he said, okay, it's a bit bigger than the natural numbers, but how can I name it? He just named it whole numbers. So he's just put a 0 in front of that group. So now you've got 0, 1, 2, 3, 4, 5, 6. So those are what we call whole numbers. So if someone tells you X is part of whole numbers, then that means X can be 0, can be 1, can be 2. Whereas if someone tell you use X, but X has got to be a natural number, then you know it's not going to be 0. Okay. After that, you've got all these numbers, but someone came up with, oh, what happened when we use a thermometer? So we can be at 0 or positive, but what happened when it's too cold? We go below 0, right? So they needed to find numbers and to put something with them. So what did they call those numbers? Your negative numbers, yeah? So if it's cold, you say, oh, it's -5, yeah? -5, sometimes you hear people. So then they came up with, you've heard about integers, your math teacher telling you about, oh, we're going to use integers today, we're going to work on integers. It just means that all those natural numbers that were positive, we're going to make them negative. So they've added all those. So now in your integers, you've got the negatives, you've got the 0 plus all the positive. So you can see our set is just getting bigger and bigger. From natural, we went to whole numbers. From whole numbers, we went to the integers. And then someone said, but what if I've got a half of something? How do you write down a half? 1/2 or 0.5. So someone said, oh, we need to add decimal numbers here. Okay, and that's when they said, okay, any number that you can make as a fraction, like 1/2 or 3/4, 3/4, we need to add them into that list. And they came up with what we call rational numbers. Basically, ratio is a fraction, something of another fraction of another number. Okay. So in those, any numbers that you can write as a fraction belongs to it. So 0.6, you can say 6/10 or 3/5, 55%, 0.55 or 55/100. So those are all the rational numbers. And even your number, a number like 5, you can write it as a fraction because it's 5 divided by 1. So that was the set of the rational numbers. And then someone came and said, yeah, but what happened if I've got square root of 2, for example? Where do we put those numbers? Because it's not a finite number. Remember when you did your Nat 5, your teacher calls them, start with an S, S-U-R, surds. So someone said, where do we put the surds? So the surds, someone said, okay, you know what? We're going to call them real number. Any number that we think is real, possible, even pi, you know, pi is a real number, 3.1415, blah, 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 infinite number. is what we call real number. Okay, so now we've got all our sets. We started with the natural. They fit inside the whole numbers. Then the whole numbers fits inside the integers. Then the integers fits inside your rational numbers. And the rationals, they fit inside what we call real number, any number. Okay, so if we were to represent that, it would look like this. So these are your real numbers. Okay, a big set of all the possible numbers. Inside those real numbers, there is a set that we call rational numbers. Inside that rational numbers, there was another set we call integers. Inside those integers, there was another set we called whole numbers, and your natural numbers, which are 1, 2, 3. So you can see that they all fit into each other. Okay. So we call them subset. So the natural number is a subset of your real numbers, for example, because it's part of it. So the members of real numbers, which are not inside your rational numbers, are what we call irrational. Sometimes you hear a teacher telling you, oh, this is an irrational number. Doesn't mean that it's not rational. It is not rational because I can't write it as a ratio. Okay, so anything like your surds, like √2 or cube root of 5 or pi, will sit in that periphery here outside the rational numbers. Okay. Okay, so to show that a particular element belongs to a particular set, the first symbol that you need to use is like a euro sign, like an E, and that means belongs to. Okay, so for example, here I've got 3 belongs to the whole numbers. So when you write something belong to, you use that E sign or the euro sign. And if it doesn't belong, the same way when it wasn't equal, what did you use? When it was equal, you put the equal sign. When it was different than, did you just you stroke the equal sign? And it's going to be the same. So if you've got a number that doesn't belong to a specific set, for example 0.9, you would just say, I don't know, a half, for example, doesn't belong to the natural numbers. So you would write it as doesn't belong like that. You just put a strike through it. Okay, so far so good. We've got different sets and we know each number's where it should go. So examples, if someone gave me x belongs to all the whole numbers, but x is less than 5, so you know your whole numbers start from 1. So that set here, you would write it as 0, 1, 2, 3, 4. You're not going to include 5 because it's strictly less, not less than or equal. Remember your sign here, less than, like that, less than or equal with a wee bar underneath it. So this is how I would represent that set of x belonging to the whole numbers, but x less than 5. So I've got another one here, x belong to the group of all integers, but x is greater than or equal to -6. Okay, so how would you write that set? You would put equal, open curly, yeah. So this time we need to start from -6 because it's greater than. So what's greater than -6? -5, then -4, -3, -2, -1, 0, 1, 2, 3, and so on. So you can see that dot, dot, dot just means to the infinity. So you would write it like that, -6, -5, -3, and then just put dot, 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 dot. It just means all those numbers after, okay? So that's how you specify a number. Here, I've been told that x is a real number, but x times x is equal to -4. What number can you time by itself to give -4? So remember, if I do -2, when I was at school, I was told that a -2 times a -2, negative times a negative was a positive. So that would give me +4. So -2 doesn't work. 2 doesn't work either, because +2 times +2 was 4. So this is a particular set, but we call it an empty set because it's got no solution. So in the real world, there is no solution that would give me x squared equal -4. Okay, so you would write it as open curly bracket, close curly bracket with nothing in it. And that just means empty set. I don't find a solution for this. Okay, so, or sometimes you see what we call the empty set. They use like phi. It's a Latin, a Greek sign. So phi is the set of an empty set, basically. So this set, and it's called the empty set. No elements in it. Okay. So now, what are functions? So now that we know how to put our elements into different sets, we're going to use functions. You've done functions, right? Y equal f of x. That's what you used to call a function. Yeah. So function describe how one quantity relates to another. What do they mean by that? Y as a function of x. If f of x is double x and take away 3, then that means f of x equal 2x minus 3, or y equal 2x minus 3. So you can see that the function that we've done describe the quantity y that relates to x, because it's double x take away 3, for example. Now, think about it. It's a bit like if the function was your assembly line and you put something at the front. So if you were to put car parts at the front, these are your x's, and you've got an assembly line in between. What comes out? The cars. Yeah. So y is the car. It is a function of all of people in between, or the robots sometimes that they use in factories nowadays. Okay. So you would get cars. So that could be a metaphoric way of expressing your function. So a function or mapping is a relationship between two sets in which each member of the first set is connected to exactly one member. So this is the important bit. So in order to say we've got a function in the engineering land, any number that you put here, it's got to be used. We can't have a part here that's not going to be used. So that's how we define the function. So let's see how one quantity relates to another. So if you've got a washing machine, for example, and you put dirty clothes at the front, your function is to wash the dirty clothes. And what would be the outcome of it? Clean clothes on the other side. Okay. So there you go. You've got your function. We call it f of x. We put n, we process it, and then we've got out what you've called at school y. So y equal f of x. And that's the role of the function. So if you're wondering, why were you doing all these? Where would you use it? So that could be something, a function, process something to give me something else on the outside. And when you're going to work with electricity or electrical signal, you're going to put something in. You're going to have a function that will process that and then will transform it into something else outside. Yeah. So it's the same like if you come with digitized signal, like zeros and ones, like on a CD, then you put it onto a player, and those zeros and ones are processed through your functions. And what do you get outside your CD player? Music. So Y will be your music, and X would be your data that is put. So any signals has been digitized, like a wave can be represented with zeros and ones, and the function will process all that. Okay? And here you could have a lot of electronic components that are all built into a chip, for example. And this could be what we call your transformer. So it will transform an analog signal into what we call another analog signal that you could listen to. Okay? And that's what they do. The chips are just massive functions that process data in and just gives you a data out. And some chips would have a sensor, for example. So if this was put onto my dashboard system to sense any shock, so imagine you've got an accident. So this is smart enough to sense how big the impact is, change the signal into an electric signal of the impact, and tells it, okay, now, because the impact is so strong, you need to fire the airbag, for example. And that would be the outcome from the impact. And these are the chips that will decide. They complete all those functions. So you can see there's functions everywhere. Okay. Okay, so a function can be thought as the relationship, like we said, of input versus output. So the function will deal with that in between. So it's as if we've got a black box in the middle, put in something, get something out, and the function is usually what we used to call x coordinates, and the output after you run it through your function would be your y coordinates when you were to represent it into a Cartesian x and y. So for every x you had a y correspondent to it. Yeah. So if x equals 0, for example, so 0 plus 0 makes 0, then that means y equal -1, yeah, or -1. So for your variables, we call that domain, right? When you come, can you put your name in here, please? So just put your name, your email address, and then what math level you've got just now, okay? So we call that the domain. That means everything that goes in. And for the output, we call it the image. So what's the image of what I've put in? Or the range. What is the range of my output? So let's see these. If I tell you f of x is 3 times x, my input is 4, what do you think the output is going to be? So if x, if x equals 4, 3 times 4 gives me 12, yeah? If x is 5, 3 times 5, 15. And if it's 6, my function f of x will change that into 18. So if my domain was 4, 5, and 6, the image or the range that I get is 12, 15, and 18 based on that function. Now, I've given you the output, yeah? And I've told you that my x's belong to the whole numbers. It's got to, in order to become a function. If the output is 36, what is the input? 6. So you've just taken the square root of 36, yeah? Because 6 times 6 gives you 36. So if the output is 49, 7 for this function, and if the output is 64, 8. Okay, so with an input of 6, 7, 8, I've got 36, 49, 64. You could have come and said, if I hadn't put you this, you might have said, yeah, but what about negative 6? Because negative 6 times negative 6 is 36. But remember what we said for the function? Every input needs to have one corresponding. But because I've decided, I'm just going to put here the whole numbers, then 6, 7, and 8 here. So you can represent it with bubbles like this. You can represent it with wee boxes, or we can just represent it with an arrow. So if the function here is 4 times by 4, take away 1. You want to grab one of these to be your teaching material? So we page 4, I think, just now. So if I time by 4 and take away 1, so what do I get? 4 times 0 minus 1. So negative 1 here. 4 times 1 minus 1, 3. And then 8 minus 1, 7. Okay, so you can see by using the function, you can go from an output to figure out what the input is, or from the input to the output. Okay, so we can illustrate them in 3 ways. By a formula, like we've seen, f of x equal 3x minus 1. By an arrow diagram, input arrow, or by a graph. Remember every time you were doing the graph, x and y? So, example, suppose that I've got a function defining a set A, giving me, so the domain would be A, giving me an image of B or a range of B. And we've been told that the set of A is made up of 5 numbers. These are integers. So negative 3, negative 2, negative 1, 0, and 1. So if f of x is x squared plus 3x, what is going to be the image for this? So I apply the formula to every input. So I get f of minus 3 or f of negative 3. 3 times negative 3 is negative 9. Negative 3 times negative 3 is plus 9. Plus 9 minus 9, 0. Do the same for f of negative 2, give me negative 2. Negative 1, I get negative 2. So you could have the same answer. And then f of 0 is 0. And f of 1, 1 squared plus 3 times 1 is 4. Okay, so you can see that the output could be the same answer based on different input. So now my range here is going to be made of negative 2, 0, and 4. So you don't need to write negative 2 twice. You just put the set is made of only 3 numbers for this function here. If I plug in set A. Okay. So what do they mean by mapping? So a mapping is made up of 2 sets. So you've got your input set, your output set. So it's exactly the same thing. So the set of all inputs is called the domain, and we said the set of all output, we call it the range or image. Sometimes you'll hear me say. So this is what we said for this set A. If I've been given 1, 2, 3, 4, 5 for my inputs, this set represents the domain. Now this set relates to an output of negative 1, 1, 3, 5, 7 by the rule double x take away 3 So if I do double 1 and I take away 3, I'll get -1. Double 2, take away 3, I'll get 1. Double 3, take away 3, 6 minus 3, I'll get 3. Double 4, yeah, and so on. So you can see what the output is. So like we were representing it. So I've got 1, 2, 3, 4, 5 here. And for every one of them, I get a corresponding value. So I've got two sets, what we call a domain, what we call the range. Inputs, domain, range, output. Okay. So basically, if you were to use this as a rule, the rule tells me that for every value of A that I put in, I need to double the value and take away 3. So you can write 2x minus 3, or you can write 2a minus 3, or it doesn't matter, as long as you know that your set are all these numbers here. Okay. So A are the elements in capital set A. So usually you'll find out a set is represented by a capital letter, whereas the elements inside, they use like small letters. Okay, so function. So let's say I've got here inputs and outputs for my functions. F of -3. So I've got two sets. I've got a function in between them. -3, we said f of -3 is going to be 0. F of -2 will be -2. F of -1, f of 0, and f of 1. So every element from my set, which we call the domain, will correspond to a value there. So 0 is the output, -2. Because I've got -2 again, I'm not going to bother because I've already got 0. I'm not going to bother because they're all the same. So you just put them there. And the last one is 4. So I started with the domain that big, and you can see that the range is just 3 of them because a couple of them share the same output. Yeah. And if you were to put arrows for this, you just put the arrows to show which one gives you what output. So that is a function. So what you need to remember is a function, every number has got a corresponding output. If I had a number on its own here without an output, then we wouldn't call that a representative of a real function. Okay. So in a graph, remember I said we can represent them with bubbles and arrows, or we can represent this in a graph. So I've got a graph here, x and y. So the standard is to have x your horizontal line and y your vertical line. Yeah. So that's what they call the Cartesian way of representing data. And you've got a right angle between them. Okay. So it's just the standard that mathematician decided, x on the horizontal line. And what you need to be very careful with is when you represent the graph, you see that gap should always be equal from the 0 and the same on that side. Okay, and the same gap here. The interval between two numbers should always be the same. Yeah. So we said that when x equal -3, I had y equals 0. So it's just the same way as your xy coordinate. That was one point. The other point was when x was -2, I had y equal -2. So you can represent that point. I had a -1 on x and a -2 on y. And then I had a 0, 0. And I had for x equal 1, a 4. So you can see here, y equals 0 for two numbers, y equal -2 for two numbers, whereas y equal 4 for just one number. So that could be another way to represent it using your graphs. So this graph consists of 5 points, and you can see it's not a solid curve, it's just points. So you don't need to link them together because that's not what they've asked us. They've just asked us to represent. So we've represented the function using x and y coordinates on a graph, or we've represented it using bubbles. So now, how do you recognize a function? So you need to tell me, I've got this example here with a set A, set B on the left-hand side. Which one is this a function? Okay, so I've got A that correspond to one value. I've got B. What's the problem with B now? It's got two values. So there's not a function that would give me two output. So in engineering math, we don't call this a function because we've got a data input that are going to give me two answers. Can you imagine if this was your airbag system and you had programmed it as a function that sometime a noise could make it to fire your airbag system? That would be disastrous if you're on a motorway at 870 miles an hour. So then that would mean this function is not what we call a function in the engineering land. Okay, because every input should only work with one output. Okay, what about this one? Is that a function? Why? So we said that a function is defined if every input has got one answer. So we didn't use G, that's fine. As long as every input has got its output and only one output. So B, C, and D share the same output, but that's fine. Okay. So this is not a function because we've got two arrows leaving B, whereas this is a function. Every input will give me an answer. Okay. What about this? Is this one a function? No, because D has not given me an answer. When I put D in, I don't have something, so again, so that would be not a function. D is unused. What about this one? Every input gives me an answer. We would call that a function. Okay. Yes. So how would you recognize a function from a graph? Remember, we can use x and y coordinate. So from a graph, if we have a function, every vertical line we could draw should cut the graph only once. Because imagine if you've got x with all the numbers, that means if I draw a line with a ruler from an x point, it should touch the graph only once. Because if it touches it twice, we're back to one input with two different output, and that wouldn't be a function. Okay, so this basically means that every x has one and only one value. So let's see this graph. So if I was to draw lines, would every x get one value? Yeah, so this one would get this. This one would get this answer, yeah. This one as well, this one as well. You can see that all of them here have only got one output, yeah. Then we call that a function. So if you're given a graph, and for every line that you can draw vertically is only touching the graph once, then you call that a function. Or this one. So if I was to draw a line here, I would touch this point and this point. So you can see now this X input has got two outputs. So would that work as a function? No, because there's quite a few places where you keep getting two answers. Okay. So we said that this is not a function because you're cutting the graph twice. X must map to one value of Y only. What about this one? Is that a function or not a function? It's not a function again, because there'll be places where I've got three answers. Yeah. So in here, if they had said to me, oh, your domain only start from X greater than, let's say this was 5, then you could say, yes, I've got a function from 5 onward. But if it's the whole line, you can see that there's a region there where I'll have 2 or 3 answers. Okay, then we don't call that a function in that region. Okay, whereas back to here, we're again just having one answer. Okay, so you could have a way to be able to quickly find a function or not. What about this one? Remember, you've done parabolas. Yeah, so is a parabola a function? So if I was to draw, yeah, if I draw a line, I'll only cut it once, yeah, with my x's. Everywhere I go, it's just cutting it once. So a parabola is a real function, and you'll use that quite a lot. You'll find out in your physical things that you'll be working on. Okay, it's a good function. Now, in your teaching material, to practice what we've been talking about here, there are 5 exercises. Okay, so you would need to do that at home as a homework. Okay, so for example, I can show you the first one where it says list the following sets. So the set of whole numbers between 2 and 10. So that one, you would open the brackets, whole numbers between 2 and 10. So you would say 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be your answer. So for question 2, list the following sets. So I've been told that X belong to integers and X is strictly less than -3 and strictly less than 4. So you would go -2, -1, 0, 1, 2, and 3. Yeah, by brackets. So that would be your answer. Now state the range and produce an arrow diagram for each of the following functions. So we've been given a function that does f of x equal 2x squared. Okay, and you've got a domain based on 5 numbers, -2, -1, 0, 1, and 2. So f of x is 2x squared. So this is worksheet 1. That means for -2, I'm going to have -2 times -2, which is 4. 4 times 2, that's 8. Okay, so I'll have 8. You do the same for -1. For 0, it's going to be 0. For 1, and then you can state and produce the arrow diagram for it, just the way we've been doing it. Then which of the following could represent a function? So we've done that. And then at the end, you'll have a couple of graphs, and you've got to state which one is the function and which one is not a function. So technically, that shouldn't take you more than 5-10 minutes to do. Okay, based on what we've seen so far. Okay, guys, so Now I'm going to give you, I'm going to pause the recording. And give you 5 minutes break. Okay, guys. And then that means we can come back in 5 minutes.